Okay, so welcome to my presentation on adaptive temporal causal network models for human synchronization and social bonding. In my presentation, I have two parts because I essentially have two topics. The first one is about two agents, and it focuses on the scenario of tapping activity. And it has both Hebbian and homophily adaptation with adaptive speed and adaptive world state. Everything will be explained, of course. The second part deals with four agents, and it has two social scenarios that will be explained, and it has both Hebbian and homophily learning and adaptation, but the homophily will be the focus. And it also has adaptive speed and adaptive tipping points. Those are just broad understanding of what the two things will be about. Before I can go into the models, I have to explain what Hebbian learning and homophily adaptation are. So Hebbian learning is a type of synaptic plasticity when two neurons are active consistently and in correlation. And connection gets stronger if one neuron repeatedly activates another while both are active. And there's a quote by the person who invented Hebbian learning, Donald Hebb, that says neurons that fire together wire together. The homophily adaptation, on the other hand, is a similarity between individuals that leads to stronger connection and quicker adaptation. So essentially, the more alike your states are with the person you're trying to connect with, the stronger your connection will be. And there's a saying, birds of feather flock together. In the presentation, in the models, there are various functions used. Most of them, I think you probably already know from the MATLAB modeling. It's the ID function, there's the Smax function, a logistic, there's the Hebbian and homophily for what I just explained, step one, step mod, and there's two new ones. So there's the BPM, which will be used in the first model. It generates pulse-like pattern for the world state, and I will show you what it looks like so you have a better understanding. And then for the second model, for the adaptive tipping point, there is the simple linear tipping point function and a new updated version, which is called the logistic tipping point function. And the difference between them is how you find the norm. It's one of the parameters of the function. The norm in the SL tip is found by finding the average incoming connection rate, while in the logistic tipping point, you find it by using the logistic function. And I will show you how to find it. So the first model, as I said, contains two agents, and the scenarios there is the tapping activity. The agent A is the adult, agent B is the student. The point of the scenario is for the student to learn from the adult. So the adaptation should be more from the student side rather than from the adult side. This is the graphical representation of the model. As we can see, we have the base level. In the base level, we have, you can see my pointer, right? The cursor. Yeah. So on the left side, we have agent A. On the right side, we have agent B. So this is adult, this is student. They have the same mental models, and they both affect each other. So we start with the world state, and that's the beat. As soon as it starts, both of the agents sense it, then they have sensory representation of it, and then they prepare to execute it. So they prepare to repeat the beat, repeat the tapping, and then they have a belief of that action, so they comprehend their own actions. At the same time, while the other agent is doing it, they receive the stimulus from the other agent. So they receive both the beat from the world state, and then they also receive the beat from the other agent, and they sense it, they have a sensory representation of it, and then they also have the belief of, they essentially comprehend it. And that's essentially how the base level works. In order for several parts of it to be adaptive, not constant, and more realistic and more close to reality, there are verification levels. So first verification level contains the Hebbian learning and the homophily adaptation, and the blue lines represent where it gets the information, and the red line represents what states it affects. In order to make the world state adaptive, to make the beat not just like essentially a straight line, but constantly alternating and have different frequencies, we have the BPM self-modeling state for the function BPM function, and it has two inputs from self-modeling states A and B, which are the self-modeling states for the world state. And they are essentially two different frequencies. I will show you in an image what they represent. And the second verification level contains the adaptive speed, and there's adaptive speed for both the Hebbian learning and the homophily adaptation. As I explained earlier in the scenario, in order for the scenario to work, we want the student to have a slightly higher learning, and of course the adult would have slightly lower learning. And then homophily AB means A affecting B, or B adapting to A, and we want that to be higher because we want the student to have a better adaptation to the adult. For the timing characteristics, all the states have essentially the same speed of 10, but the speed of the adaptive speed is much slower because we first want to make sure the adaptation happens, the learning happens, and then we can adapt its speed. This is the simulation result of the base level. I won't be showing all of the states because it's just not very relevant to the final result. It's essentially just to show that all the processes are happening correctly. But as I said, I wanted to explain how the beat works. So this is essentially the self-modeling state for the self-modeling state A for the world state, and this is the B part. You can see the big difference in the change in the frequencies. Also from this graph, you can see that the sensory state, sensory representation states of both agents in response to the world state are very in line with the world state, which means that everything is good with from the very beginning, with the agents being able to comprehend and sense the beat. This already is the simulation results of the Hebbian and homophily adaptation. We can also see the speed adaptation in here. This only is here to represent that the speed in the beginning is a bit chaotic because it's trying to learn at the same time, but over time we can see sort of a consistent pattern of constantly alternating up and down speed. If we look at the Hebbian and homophily adaptation, we can see that the Hebbian B, which is the student, has a higher level of learning as was in the scenario, and also the adaptation by student to the adult is higher. The beginning is a little bit messy, as I talked about here. That's because it needs time to adapt it. It needs time to learn. If right away the curve went all the way up, that would have been very bad for the model because that means there's no learning happening. It happens right away. In order to evaluate the model, several connection links have been modified, and this is the explanation of them. So first we have the prediction link. It's this one right here. It's how well the agent is able to predict that a stimuli will be coming towards them. Perception sensitivity link is how able you are to actually perceive that stimulus that the other agent is creating. The belief of perceived stimulus link is how you're able to comprehend it, and then the same thing here is how able you are to comprehend your own actions, which is the belief of own execution link. And then lastly, the expressive link is how much effort you put into expressing the stimulus so the other person can hear or see the beat, sense the stimuli. After doing all of these modifications, the conclusion I came to is that the Hebbian learning is influenced mostly by the prediction link and the belief of perceived stimulus link. And then because slight changes in these values already create a big difference in the behavior of the states and of the adaptation and learning. Links such as perception sensitivity link, the belief of own execution link, and expressive link can be kept at 0, and it didn't create a much or any significant effect on the learning. For the homophily adaptation, important links were the belief of own execution and the expressive link. And again, the perception sensitivity link could be kept at 0, and it didn't create a big effect. Just to point out that this model was based on a model created in 2018 by Michael Aceto, and the difference between them, the improvement, was that I added more base level states. So there's sensory states and belief states, which approaches more to a realistic representation of the mental modeling process. And also there's adaptation for the beat and varying frequency, as I showed you. And also there's speed adaptation of the speed factor for the learning and the adaptation. Now we're moving on to part 2. The second model that I built deals with 4 agents and its social activity. We have 2 scenarios. The first scenario is trying to exclude an agent. So out of the 4 agents, agent D is trying to be, the 3 agents are trying to exclude agent D and not letting it adapt to everyone else. And then in scenario B, we have just a group project dynamic. That no one's really trying to be excluded. It's more like by the parameters, I tried having A and B have stronger links with each other and C and D having stronger links, like as in they're 2 friends and 2 friends, but they're all working in a group. And the thing is that they have also different expressive links, and we're going to see how that affects the dynamic of the group. And in this model, there are going to be 2 functions. It's going to be modeled using 2 functions, and it's not really to compare it, it's just to show there's a way to do it like this and a way to do it like that. This is the graphical representation. It's a bit confusing, so I will split it up and explain every section bit by bit. So first we have the base level, and the base level, it's exactly the same as we saw in part 1, except now there's twice as many because there's 4 agents. What is new is there are new sensory states, sensory representation state, and belief states for every pair of connections. Yeah. For the first verification level, there's Hebbian learning state and homophily adaptation state for every pair of adaptation. The same thing goes for the adaptive speeds. And the new thing here is the adaptive tipping point. So there's adaptive tipping point for every agent. And the tipping point is essentially like a tolerance of how the agent wants to receive information. So if the tolerance is very high, that means they're very picky about all the information they want. And then if the tolerance is very low, it's they're more accepting all the information. And by making the tipping point adaptive, we're essentially making the tolerance go up and down all the time to make it more natural. On the very top, you can see a context state. The context state is essentially like a personality characteristic, and it represents how far someone prefers to have the bonding. In this model, it's not very much experimented with, and it's perhaps something for maybe future studies, but it is included in here. For the scenario A, again, where we're trying to exclude agent D, the links towards agent D are very weak, as we can see highlighted in yellow. And agent D won't be able to receive information as well as the others. The links are not at 0, but they're very, very weak. And this enables agent D to share his information, even with a bit of a weak expressive link. But the problem is he cannot receive hardly any information from others. In scenario B, for the connection weights, we can see stronger links between A and B and stronger links between C and D, but then we can see varying expressive links. So for example, A has strong one, but B has a weak one, and we're going to see how it affects their interaction, how the adaptation from A to B is different from B to A, or even to other agents. In the aggregation characteristics, as I mentioned before, Hebbian learning is not really experimented with, so all of the values for it are near 1, so near perfect, but they're all different, like 0.95, something like that, to make them all unique. For the homophily, alpha is the amplification factor, so how much the effect should be amplified. It's kept at 0.1, and the tau, which is the tipping point, is adaptive, and that adaptive tipping point has 2 parameters, the alpha and the norm. The alpha is the amplification, so how much we want to amplify the tolerance, and the norm is kept at 0.4, and this is just the way I found it. For the, as I mentioned before in the functions, to find the norm for the SL tip, you have to find the average of all the connection weights, which we can see right here for scenario A. Same thing for scenario B, they're both at 0.4. And for the logistic norm, logistic tipping function norm, we use the logistic function, which the result is also 0.4, can be seen here. The alphas for scenario A is just kept at 0.6 amplification, but for scenario B, there's variation between agent A, agent B, C, and D, and we're going to see how it affects the outcome. So here we can see the homophily results for scenario A. The goal here was to weaken the adaptation for D, which was successful. D, it's not very clear, but I will just point with my cursor that all of these lines on the bottom right here, they're all adaptation by agent D. So agent D was not able to adapt to A, nor to B, nor to C. Interestingly, what I wasn't trying to find, I wasn't expecting, was that C had the strongest adaptation in both graphs, in both functions, SLTIP and a logistic function. And I found that that was because there's a strong within agent link connection between agent C and the other agents, and also agent C themselves has a strong expressive link. And overall, as I said, I won't be comparing the two functions, but I just want to emphasize that they behave very, very similarly. It's just different ways of showing this model. For scenario B, in the simulation where we had 4 agents and we are trying to show a dynamic of a group project, interestingly, some things did not track and did not go along with the way scenario A worked. And I found out that the strongest connection actually happened when there's medium connection weights between the agents and strong expressive link. While the weakest actually happened when there was a strong connection weight link, but weak expressive link. And in some cases, even there was one connection where there was a strong connection weight link and strong expressive link. And that was almost here on the very bottom, which was very surprising to me, not something I expected, and kind of emphasizes that homophily can act in its own way. But one factor that I thought may have had a strong effect on such outcome was the amplification factor for the tipping point, which was these values right here. I found that if the alpha is very high, which was the case for agent A and D, there's a weaker adaptation. So in the summary, the first scenario showed successful adaptation among agents who possess strong within agent links and expressive links. That did not really follow for scenario 2 because there are more factors, and there could be strong within agent and links and expressive links, but adaptation could be weak. But as I said, what seems to be the problem, but of course more experimentation has to be done, was the strength of the amplification factor for the tipping point. And this model was based on Jan's 2020 model from his book. And there were 10 agents and only homophily adaptation, and there was adaptive tipping point with the SL tip function. My model has a little bit less. It has 4 agents. However, it has both homophily and Hebbian learning. And it has adaptive tipping point with both simple linear tipping point and the logistic tipping point. And it has adaptive speed. So essentially, my models have provided deeper understanding of underlying mechanisms driving adaptive processes, and they emphasize the significance of interplay between connection weight links and function parameters. Yeah, and they can be used for, of course, more studies can be done. As I said, more experimentation can be done with the amplification factor, also with the context state. Other parameters can be also adapted or modified for better results, I guess. But yeah, thank you for your attention. And are there any questions?